Scale-free networks. Networks like this are generally represented as scale-free networks. In this network, you may find some nodes with very heavy connections like this. These nodes are called hubs. Hubs are defined as nodes with very heavy connections, or if we represent such kind of networks through XY plotting, with Y plot as a number of nodes and X plots as a number of links, then we will get a curve like power law distribution. In this part of curve, we will see very few number of nodes with very heavy links. And in this part of the curve, we see that very few links. If we represent this plot as a log scale with the same y and x coordinate, then it will give a straight line like this. While networks like this is called random networks. For example, connections of different cities by road, traffic, etc. In this kind of network, the connection depends upon some local or global demands. If we represent such kind of networks through XY plotting like this, then we will get a whale-shaped curve like this. This portion will show some typical nodes. Most of the nodes have same number of links in this portion, and in this portion we will get no highly connected nodes. Scale-free networks, preferential attachments. It is an important characteristic of scale-free network. Preferential attachment means new node tends to connect to nodes that are already well connected. This will clear from this example. Suppose we start with a node and connect with a new node. Then at second stage, now I will add a new node. Then now at next stage, suppose we want to add another node, then it will search the node which is already highly connected like this. Now at next stage, suppose I want to connect a new node, then it will search the highly connected node like this and make a connection. Now similarly at next stage, it will treat like this. Similarly, we can increase the size of network by adding new nodes, and every time the new node will search the highly connected nodes or hubs. In random network, the connection depends upon the random or local or global requirements. Suppose we have two cities like C1 and C2, and we have to add two more cities like C3, C4. Then there may be a network like this. It depends upon the local demand. The two mechanisms, growth and preferential attachment, helps to explain the existence of hubs. As new nodes appear, they tend to connect to the more connected site. As we have seen in this example, every new node searches the highly connected node for a new connections, for a new links. Thus, it favors the concept like rich get richer. Scale-free networks, degree distribution. In undirected networks, the node degree of node n is the number of edges linked to n. The node degree distribution gives the number of nodes with degree k for k is equal to 0 to 0, 1, 2. In directed networks, the in degree of node n is the number of incoming edges, and the out degree is the number of outgoing edges. Similar to undirected networks, there are in degree distribution and an out degree distribution. Baravasi and Albert used the node degree distribution and to distinguish between random and scale-free networks. Scale-free networks the degree distribution of scale-free networks follows a power law. Can be explained like degree distribution implies that where k can be m to capital K. Here m is the lower cutoff for the connectivity, and K is the upper cutoff for the connectivity. C is a constant and it can be estimated as it is also known as normalization factor. It has found that in most of the scale-free networks, the exponent lambda lies between 2 and 3. Now the question is it possible to get any relation for K? Suppose we have M, that is lower cut of the connectivity, N, total number of nodes in the network, and lambda is given. Actually, in all real life networks, they are finite, they support finite moments. Thus, the actual value of cutoff, small k, plays an important role. It may be approximated by total probability of nodes with k greater than capital K, and is of the order of 1 by n, and it can be obtained by using the integration of with limit k to infinity on solving. We will get a relation between k and relation for k. Other definitions of scale-free network. Lee et al. 2005 offer a scale-free matrix. Let G be a graph and E represents edge set. Then for node I and j, suppose this represents node I with some degree of, and this represents node j. We represents the degree of node I by di and represents the degree of node j as dj. Now, according to this matrix, Sg, which represents the scale-free matrix for graph G, can be given as Ij is member of edge set E. This will be maximized when high degree of nodes are connected to other high degree nodes. Now, to normalize this factor, this equation, we will use where S max is the maximum value of SH for H in the set of all graphs. The set of all graphs with identical degree distribution to G. This matrix gives value between 0 and 1 such that graph with low Sg are scale rich, and graph with Sg close to 1 are scale free. This definition also captures the notion of self-similarity. The strength and weakness of scale-free networks. Scale-free networks are extremely tolerant to random failures. For example, suppose nodes like this, such nodes fails, then it will not affect the entire network structure. While in random network, a small number of random failure can collapse the entire network. For example, suppose nodes like this and this fails, then it will divide the entire network into two parts. A scale-free network can absorb a random failure of up to 80% of its nodes before it collapses. The reason for this is inhomogeneity of the nodes on the network. Failures are more likely to occur on relatively small nodes like these side of small and outsider nodes. Scale-free networks are extremely vulnerable to intentional attack on their hops. For example, suppose we attack on this hub and this hub, then it will create several islands of isolated nodes. For example, this node, all nodes will be disconnected from the network structure. Attacks that simultaneously eliminates as few as 5 to 15% of scale-free networks hub can collapse the entire network. A scale-free network can heal themselves rapidly if an insufficient number of hubs necessary for an systematic collapse are removed. Now, other thing is the scale-free networks are extremely vulnerable to epidemics. For example, suppose we plan a virus attack or any epidemic attack with this node, then we can easily reach to most of the nodes very easily. While in the random network, suppose we plan in this node or in this node, then to reach at most of the node, it will take a lot of time and we have to cross a lot of other nodes. In random network, epidemics needs to surpass a critical threshold, a minimum number of nodes infected before it propagates system-wide. Below the threshold, the epidemics die out. Above the threshold, the epidemic spreads exponentially. There are some examples of scale-free networks like cellular metabolism, in this network, molecules involved in burning food for energy, behaves like node, and links like participation in the same biochemical reaction. In Hollywood network, actors behaves like nodes, and links represents its appearance in the same movie. Similarly, in internet, routers represents the nodes, and optical and other physical connections represents the link. In protein regulatory network, the proteins that helps to regulate cells activity represents the node, and interaction among proteins creates the link. Similarly, in research collaborations, scientists will act as nodes, and their co-authorship papers will create the link. For example, paper 1, this is a main author. In paper 2, there is a citation. then it will create a link. In paper 3, suppose S1 is a co-author, then it will create a link. Similarly, in World Wide web pages will create nodes, and URLs will create the links. Degree of separation. The least amount of links between two nodes is called their degree of separation. For example, if we have a network like this, then the degree of separation between 1 and 7 will be 3, because we will travel through 1 to 2 and then 2 to 5 and then 5 to 7, and it is the least number of links between 1 and 7. So the degree of separation of 1 and 7 will be 3. The concept of degree of separation is further used in the description of a small world network. Another example, suppose we have a network like this. Then the degree of separation will be between A and C will be 2, because there is no direct connection between A and C, and so we will use the minimum number of links first and second. So the degree of separation between A and C is 2. Suppose a person P1 is in India and a person P2 in South Africa. To reach from person P1 to P2, how many intermediate people are needed to connect those two people? To answer these questions, Stanley Milgram had done an experiment. Milgram sent mails to random people in Kansas, suppose represent as TA in Kansas, and Nebraska, and asked them to address the mail to their acquaintance who may know the target person in Boston. After the entire experiments, he found that average number of intermediate people was just 5.5. Means just after 5 links, the mail reached on average 5.5 link mail reached from Kansas or Nebraska to Boston. Now the question is, first, is the 6-degree separation is reasonable? And other question is, suppose there are 7 billion people in the world, Then is the 6-degree separation will work here, or in other words, how many people should one person know so that all people in the world become completely connected? Now suppose every person knows on average 50 different people. Then at degree 1, the person will link to 50 different people. Similarly, at degree 2, the person will link to in the world. Similarly, at degree 3, it will link to different people in the world. And finally, at degree 6, it will link up to 15.6 billion people. Thus, the 6-degree separation are enough for 7 billion population in the world. It also supports the 6-degree separation or the reasonability of the concept of 6-degree separation. Formal description of small world networks. Suppose each node has on average k links in the network. Then at first degree, the node will reach up to k link, and at the second degree, it will reach up to k square nodes. Similarly, at the third degree 3, it will reach to k cube nodes, and finally at degree D, it will reach up to k to the power d nodes. If k is big, then the number of reachable nodes become very large, even if d is small. Now calculating the average distance. Let n be the number of nodes in the network. Then we can assume k to the power d is equal to n. Then we can obtain a formula for an average distance d by d is equal to log n divided by log k. But in the case of World Wide Web, the average distance is 19th degree with 1 billion nodes. Actually, small world network is an important part of scale-free network, because in the small world network we generally considers the concepts of hub, means a node with large number of connections, like this. So the use of scale-free network makes the degree distances of nodes be smaller, because one person have more chances to connect other hub nodes, and thus it makes the world smaller.